Hello, I'm MC Toon, the worst rapper in the world. Tonight we've got a flat earth debate. I have with me, connected, but not visible. He doesn't have his camera going yet, but I have Wayne Chipman. How are you doing, Wayne?
Real great.
Good, good. All right. Your audio looks good. Your video is what it is. I'll get something in place for your video, or so people can see you.
You can put that one picture up with me on the other one I did with the beard and all that. That's fine.
All right.
I look goofy enough.
Yeah, that's if you say so. I'll let you stick with that one. All right. So why don't you I got to do a little moving things around. How about you talk a little bit about yourself here for a minute?
I grew up in Vancouver, Washington, one of 6 kids. My grandparents had a 160-acre farm in La Center. I loved it, loved that life. And then I just kind of, went along with my life, didn't pay much attention to anything, just work, raise a family and all that. Then probably 15 years, maybe a little more ago, I was talking to an old Vietnam vet, and he told me the truth about money. And I walked away thinking that guy's effing loony bins. He's a nutcase, but he piqued my curiosity. And then for probably a year or so, I spent studying the creation of money, our history of money and all that. It's a rabbit hole that goes endless. And then probably about a dozen years ago, I ran across a really lame video. There was hardly anything on YouTube at that time or anything about it. And it was about the flat earth. And I started studying it that night. It piqued my curiosity. And by that evening, I knew our Earth didn't spin. But it took me probably over the next year and a half before I realized that we live on a flat, motionless plane. Because back then, there was hardly any info. It's I was digging for info while Eric Dubé was, as he was writing his book. And he was always a step ahead of me. But we kind of piqued each other's interest and curiosity through a bit there. And it was a fun learning experience. And it didn't really, some people say it really changes our worldview, this and that. Is I had already discovered so much of our history by this point that it was just one more turn of the gears or whatever. It wasn't no big deal. And then after that, started joining groups, and back then it was lonely, but over time, more and more people joined and started learning of the truth, and it's been a fun ride. And I might be a little rusty right now because for probably the last 8 or 9 months, I've just been going down the rabbit hole of the current politics and satanic pedophiles that control our world, and haven't been paying too much attention to any new things coming out of the flat earth realm for a while.
Well, I can tell you didn't miss anything. There's no new science for flat earth. So yeah, you didn't miss anything.
Yeah.
Really, honestly, for the last 5 years, there's nothing. Actually, since Robotham, there's nothing new. So you didn't miss anything.
There's little things along the way, but he put out a lot of good points. And then there was another lady. Oh God, I'm trying to remember her name.
Blunt.
Yes. She was pretty good too on what she put out.
Yeah, she had the blunts. probably spliffs too, I suppose. I don't know what's what. So, all right. So you said the Earth doesn't spin. How did you measure that?
Well, airplanes would probably be one of the best proofs that our Earth is not spinning. Say you're at a air show and planes are spiraling up in the air, turning every which way, banking, looping, going north, south, east, and west. Okay, I'll give you guys relative motion. I'll give you the spinning ball, but you got to keep in mind that once this plane's left the air and made multiple turns and everything, all the while beneath it, the ground is moving at 800 miles an hour due east in America. The people on the ground are moving 800 miles due east in actual land movement. Okay, so how can relative motion keep this plane going steadily 800 miles an hour east to stay over this moving land beneath it once it's made all sorts of different turns, air brakes, you name it, back and forth, spiraling in the air, yet it always stays above the cloud, just as if the cloud were motionless below it.
Okay.
That's
Are you now? I teach. We homeschool our kids, and I'm the science teacher, so I know different levels of what thing are taught for science. So in elementary school, we teach conservation of momentum. So are you aware of conservation of momentum?
Yes.
Okay. Well, then that's your explanation there. That's pretty easy. Good. Let's move on then.
Well, let's not shy that off. If the plane is accelerating east, okay, and say we have conservation of momentum and it's going 800 miles an hour due east to that, then it's going 400 miles an hour on top of that faster if it's a 400 mile an hour airplane, which a lot of these Red Bull planes are. Okay, but when it comes back, it's going against that conservation of momentum. And so when it turns again, how can it still retain this 800 miles an hour movement when it's already went against it? It's like, it can't.
Well, that's easy. So it goes one direction. It's going a total of 1,200 miles an hour in one direction in this, this whatever latitude this would be. And then it turns, let's just imagine it's going to stop, like decelerate and then re-accelerate the other direction, right? So it will decelerate in its reference frame from relative to the ground or relative to airspeed, really, from 400 miles an hour to 0 miles an hour. And the lateral speed is now just 800. Then it accelerates the other direction. So you need the deceleration and then the acceleration. So that you went from 0 airspeed / 800 linear speed to 400 airspeed / 400 linear speed. This is all just, taught in elementary school.
I know it's taught, but in the real world, it would not play out that way. How
does that not work?
Because once it's left the ground and no longer having contact with the moving Earth, and it makes various turns and thrusts and moves, it no longer has that conservation of momentum that it had when it left the ground. It's been negated by thrust and angles and vectors and everything you want to call flying.
So
it cannot
So thrust cancels conservation of momentum?
Yeah.
It makes the law of conservation of momentum not happen anymore?
If the plane is thrusting back at you going due west or due east, and it's thrusting back at you, it's taken away that conservation of momentum it had on the ground. And then when it turns and goes the other way, how does it pick up that conservation of momentum?
It accelerates again. Because the plane has an engine. That's how.
Yeah, but we're forgetting that the ground is in a constant moving at 800 miles an hour, according to spinning ball Earth theory.
And so is the air. So it's in a reference frame. The reference frame is moving at 800 miles an hour. So you don't need to do anything. Actually, you don't even have to worry about it because you're within the reference frame.
Okay. So once this plane's performed a bunch of maneuvers, the only thing keeping it going with the 800 mile an hour land beneath it is the 800 mile an hour air.
Yes. Yep. All right. You got it.
Okay.
Good.
Well, planes, if they're in 800 mile an hour air, it would do some serious problems for them when they're turned sideways to it or banked to it.
But it's moving with the air. The air and the plane are moving together. They're in the same reference frame. Now, reference frames are not necessarily taught in elementary school, maybe in high school, but it's not really that difficult of a concept, right? Have you seen people like throw a paper airplane while inside of a bus that's moving?
They're inside a bus,
or maybe play catch. Yeah, and so that's their reference frame. They're within the bus and the air together form the reference frame, and they're moving within that reference frame.
Inside it, yes, they're attached to the bus.
Sure, yes, They're inside the
plane.
bus.
Yes, the plane, once it's left the ground, is no longer attached to the ground in any way, shape, or form.
Yeah, it's in the air, and the air is moving
Yes.
with the ground. The air and the ground
Yes.
together are the reference frame.
Yes, but that 800-mile-an-hour air that's traveling with the ground is the issue for a plane to fly in 800 mile an hour, because once it's made some turns and pressed in different positions, it's lost all of that conservation momentum. Its forward taking off speed has been negated numerous times by all its turns.
Well, yeah. So if it's going 0 when it starts, right? Because we can just ignore, because it's in a reference frame, we can ignore the 800 miles an hour. It's in a reference frame. We don't need to worry about that anymore. And I think what you're doing is you're trying to add back in the reference frame when you don't need to.
Well, the reference frame then is basically saying we're going to treat it like everything is sitting still.
And that's exactly, yeah, you got it. That's what a reference frame is.
And you don't see how silly that sounds when we're talking about 800 mile an hour air above 800 mile an hour ground.
I don't know why that's right.
To treat it like it's sitting still because it's a frame of reference.
Yeah, that's exactly right. That's how it works. Because in a bus, if you're going 60 miles an hour, you're going 60 miles an hour relative to the ground, but inside the bus, you're stationary when you're sitting there. And when you throw a ball across the aisle, or you throw a paper airplane, or you fire up a little drone and you have it hover there, it all just sits there.
You're inside
Yes, exactly. Yeah, you're inside the bus.
Touching it, connected to it.
Yeah, but the drone isn't. If the drone is just hovering inside the bus, it's not.
But it's a block of air that's moving inside a closed environment.
Absolutely. You got it. You understand now. Good.
Oh.
Good. That's how reference frames work. So awesome. We solved that for you.
Okay, we can go on to another one. That was pretty humorous.
Sorry, I had to shut the door there. Well, good. We got it. All right. So then you said it's flat. So do you have some measurements of flatness?
Well, I live at the coast, and from an elevated, probably 45 feet above sea level and about 400 or 500 yards from the beach, the actual sea surface, I used a very accurate 8-foot level, used it 2 different ways, set it up perfectly level each way, and pointed at the ocean, sighting down it. You see the ocean horizon right exactly at the top of that level, which would not be possible on a ball.
From how high?
45 feet above the ground, which at 3 miles, well, I don't know how many miles the ocean surface would disappear again.
Okay, so I'll write this down. 45 feet.
Above the ground.
All right, you're 45 feet elevation. All right, you keep talking. I'll pull up, because I'm sure you did the math too. But, we can compare the math. But you maybe, talk about how you calculated the predicted drop for the globe and the predicted drop for a flat Earth. So just a second.
The predictive drop from a level line of sight is 8 inches per mile squared, which works out to the circumference of the Earth and math. There's charts that show it. I've got them buried in my meme somewhere. But
so how many degrees drop would you expect then from 45 feet elevation? How many degrees drop would you expect?
I haven't worked out the degree drop. It'd be
so you didn't actually measure anything then?
There would have to be a drop.
That would make sense then. That's why
there would have to be a drop on a ball.
Absolutely. And so now it makes sense why you were confused, because you didn't actually do the math. So all right, let me let's see here. I think I have let's try this one here. I have a couple programs. Are you familiar with writing software in Python?
No.
Okay. Well, that's okay. I am, and I have a little program I wrote in. There it is. All right, in Python. So let me. I will pull this up so that everybody can see it. Everybody can look. I'll share it to you so you can see. Right. This will be good. Don't worry, the Python is not very complex. I keep it pretty pretty simple, and it just looks like a little bit of math homework is about it. So there we go. There's that. So everybody sees that. I need to fix the screen. It's a little bit too big. It's rolling off the screen. Ooh, how's that looking, people? There it is. All right, so now you're not seeing it yet. I'll get it so you can see it. Where did Zoom go? This will be cool. I wrote this quite a while ago, and I've not yet had a chance to use it. So you're the first one, Wayne. There you go. All right, do you see that?
I can't get your screen to grow after I went through so many things with the sign in. I'll take your word for what it says on the degree.
Okay. All right. Well,
yeah.
All right. So I'm going to do this. Now height of observer is this in meters.
So 15 meters.
Okay. 15 meters.
And about 500 miles or 500 meters, sorry, from the shoreline where the actual waves hit the sand.
Yeah. Well, that doesn't matter too much unless that's closer than the horizon, which it would not be. So, all right. So we've got the distance to the horizon, 13,800 meters, or 8.5, a little over 8.5 miles from that elevation. And the horizon dip, 0.125, 124.2. So, and then of course,
a little over 1.25 degrees.
No, 0.12 degrees, less than
a tenth of a degree.
Less than an eighth of a degree. Yeah, just over a tenth of a degree. So is the precision of your measuring instrument more or less than 0.12 degrees?
That's a tough one to call. It's a pretty good 8-foot level.
I think an 8-foot level probably is accurate to maybe half a degree. And then,
that'd be probably a fair assumption.
Yeah, so your margin of error is significantly larger than the expected dip. So that measurement isn't really very useful. Now, if you use there are better instruments for measuring.
Theodolite.
Oh, there you go. Now, a theodolite. Now there are apps on phones called conveniently enough, the Theodolite app, and now the accuracy of the Theodolite app on like my phone here is 0.1 degrees. So still at 45 feet elevation, it's not precise enough. You really want to get ideally a full order of magnitude better precision. So you'd want something accurate to 0.01 degrees. Right?
Yeah.
So a good theodolite is accurate to maybe 5 arc seconds. That's a decent one. A really good one is accurate to 1 arc second. Now, do you know arc seconds, how that works?
Yes. Okay, let's take it to another height. Have you seen the videos of the high altitude cameras on balloons?
I have, but none of them have any leveling mechanism in them. So you don't know where the eye level is. So there's no measurements in them to reference. So unless you're going to bring one, and I've never seen one, unless you can reference one that actually has either a very accurate leveling gimbal on it, and then we can use the center of screen, or a built-in level inside the mechanism. None of them will tell you whether or not you're seeing something rise to eye level. But you can do it in a plane with a phone. Because in a plane, you're looking at 2 to 3, maybe 3.5 degrees is what must happen if the Earth is a sphere, right?
Yes.
We can do the math on that the same way. So, right. So we could we can do here, we could say here, I have on here, we could do Mount Everest, which is lower than an airplane. But we can do for Mount Everest, the dip would be 2.6 degrees apparent, 3 degrees with no refraction included. So that's enough for a phone to do from Everest, or an airplane is higher than that. So what you could do then is, if next time you go on a flight, do you fly much?
No, I actually don't like to fly. Scares the living shit out of me.
Really? But you have flown.
Yeah.
Maybe
yes,
you
I have flown.
Maybe you could ask your son to do that.
Yeah, I might
you.
have him check it out next time he flies, because he flies a couple times a year. But to your eye, though, you're seeing level.
Well, our eye is. Do you think what's the precision of your eye for measuring degrees?
Pretty good on my eyes, I'd say. But no matter how high,
how many degrees precision are your eyes?
That's a tough one to call.
Yeah, I would say the human eye is maybe accurate to 5 degrees at best. But here's what you can do. Like I said, you can get a theodolite app. Now I'm showing it right now, and I know you can't see it, but let's see. That's not showing very well. Here we go. So there you go. There is on the screen now, and I don't know why you can't see it, but I have used my own phone, the very phone that I still have here, flying from Anchorage, Alaska to Minneapolis, over the Yukon Territory, just in rural mountains there, nothing around but mountains, and the theodolite. Now you can calibrate the theodolite. I did it the day before at the mouth of the Kenai River near Anchorage, Alaska. So that's the best way to do it. You go right down to the ocean. So I was toes on the water was lapping up on my toes to do this. And I leveled it here. It's I actually got it. There's two things on the screen. You can't see both of them because they're overlapping. There's a line that is 0 degrees, and then there's where I'm pointing, but they're overlapping. And funny, the horizon is below the measured eye level. Now I can send you. I'll do this so you can look at it later at your own leisure.
Yeah, if you want to go ahead and send it on my Facebook or
then I can on your Facebook. See it. And so there, if you scroll down about halfway down the page, you'll see the one I'm talking about, that I talk about where I was flying from Anchorage to Minneapolis. But that's not the only one. There is, that popped away. There it is. There's another one here by Globular Epic Bikini. At Flat Slug Brains on Twitter. Another one there. He actually pointed down to the horizon from the airplane and got a 3.3 degree dip of the horizon from the airplane. Another one from D Wolfman 54, where he pointed it straight ahead. The horizon did not rise to eye level. So those are a couple from airplanes. So you haven't measured it from an airplane, and your measurement of it was not precise enough. So did you do anything else to measure flatness?
We can go with shadows. You can take and pick a mountain or a skyscraper and put a perfect white backdrop behind you, brilliant white, and watch the setting sun on a nice bright sunset, and you will never have a shadow stand taller than you.
Than a person.
Than yourself. With a backdrop, watching a setting sun from an elevated position, your shadow will not be taller on that backdrop than you are.
What?
Yeah.
I like you stand up a board in front of you?
No, behind you.
Vertical, or do you lay it down?
Vertical. No, vertical. I'm not long.
Okay.
I'm talking taller than you.
Why would you expect?
A setting sun would be below you on the ball earth if you're on an elevated position.
Yeah, and how much?
Your shadow should travel upward.
Yeah, but here's the thing. We already determined, like, if you're 45 feet high, the horizon, the dip of the horizon is 0.1 degrees down. So that angle of the shadow, at best, at 45 degrees elevation, would be 0.1 degree angled higher than...
It would be higher.
Yeah, but 0.1. Now, the problem is the edge of the shadow, because the shadow isn't perfectly crisp on there, the edge of the shadow is going to be, the fuzziness is going to be thicker than anything about 1.1 degree. Now, so again, if you went to a high elevation, say you went halfway to Everest, and maybe you could have a 1.5 degree of dip of the horizon, right? You'd have on that shadow 1.5 degree raising as the sun set. But how did you measure that amount of? It's a pretty small amount. So did you actually like calculate how much you expect it would be taller?
No, I just know it would be taller if the ball were true.
Okay, so again, this is the same problem where you didn't actually do any measurements. You didn't quantify it. You didn't actually write like a hypothesis that if the Earth is a sphere with radius 40,000 kilometers, then at this elevation, the shadow must appear this much higher because the trigonometry demands it. You didn't do that. You just said it should be higher. You don't know how much it should be higher, but it should be higher. It didn't look to you with your imprecise measuring instrument, your eyes, that it was higher. Therefore, it's...
Okay.
Yeah.
Here's another one. Okay.
That didn't work, does it? Okay.
We stand on the seashore. I'm 6 feet tall. Say my eyes are 6 feet tall.
All right.
The horizon's at 3 miles. Okay.
Okay.
Beyond that, I start to see a ship disappear below the horizon. Okay. I wait till that ship's completely gone. All right. It's went over the curve, would you say?
Well, it depends. Did the ship get so small that you could not resolve the detail, or did part of the ship get obstructed by the horizon, and then more of it, and then more of it, and then more of it, and then it went away? Which one?
You see it start to disappear.
Okay, so part of it disappeared.
And then eventually you can't see it anymore.
And then all of it gets obstructed.
Yes.
Yes, okay.
Okay. Then I can whip out a nice telephoto camera and bring that whole ship back into view.
Oh, so do you have any evidence of this?
You can actually see a lot of the video showing it.
I've never seen one. I've seen people claim it, but every time it's not zoomed out, and what you see is the ship just gets so small that it's unresolvable. It's just too small, right? And then they zoom part way in, and then you can see it then, because now you can resolve it because of the zoom. And part of the hull is obscured. They zoom in more, the same amount of the hull is still obscured. They zoom in all the way, and the same amount of the hull is still obscured. Never have I seen zoom change how much of the hull or the bottom of something is obstructed. I've never seen that. I've seen videos. People have sent me dozens of videos. Look at this one. Look at this one. Never once have I seen that. In fact, here's the challenge. Watch the sunset. Whip out your telephoto lens. Whip out the best telescope in the world and bring the sun back. Never happens. Nobody's ever done that. Why is that?
That's because the horizon's so far away where the sun sets.
Yeah, but no. But you just claimed that the zoom will bring it back after it's gone over the horizon.
The ship.
But it's never happened.
There's plenty of video you can see.
I'll
work on gathering more of them up.
All right.
The oil platform ones is pretty cool too. We're talking miles.
Here's
miles of video.
Here's a good one we got from Mandelbrot's set. Now you live out west there, not too far from Mount Hood, right?
I could Mount Hood is it's in Oregon. I've been there. About 120 miles from it.
Okay. Well, here is I'm sending to you, and everybody playing along at home can see. Thank you, Mandelbrot set, can see the mountain as you were talking earlier about the the shadow being
Jimmy.
higher.
Grab it.
It's what you want me to give you something?
What's that?
I heard you talking to somebody there.
Oh, my friend Jimmy, I was having to grab me a beer.
Oh, Jimmy. Okay, I got a beverage too. Oh, there's two of me on screen. Do you guys see two of me? Oh, no, you don't. That's Zoom. Wow. Didn't expect that. All right. So I have right now on screen Mount Hood, and the sun is right in the process of setting, and the shadow of the mountain is actually being cast up onto the bottom of
the clouds.
Yeah. Amazing. How does that happen if the Earth is flat?
We have a rising horizon that meets the sky at our eye point.
No, but we already determined the horizon does not rise. We already determined that. I mean, I showed measurements to everybody that there is no, but the rising horizon wouldn't change the angle of the light. That's the problem.
As the sun gets further distance, the sky meets the horizon. Always has, always will. It's how refraction works and our eyes work.
Wow, this is new physics.
It's there.
It is.
It's called horizon perspective.
It is. Oh, this is totally new. But here's the problem I have with that though. If the sun is how high is the sun again?
I used to think it was around 3,000 miles high, but I don't think it's that high. No one knows its true height. In fact, its height changes as it goes from season to season above the Earth.
And you know that by measuring it?
By the different twilight they have in the southern region, south of the equator, which many people will attest to. They have a very short twilight. Where here in the northern hemisphere, we have a very long twilight.
Oh, this is new. All right. So you did not measure it. Here's the thing. Yeah, we'll get into that in a second. But the angle of the light is still the angle of the light. Whatever perspective tricks you might be thinking is happening isn't going to be changing it, because if the sun is a couple thousand miles high, then in order for the light to get to the ground, even when it's really far away, it's got to be coming down at an angle, not up, down. So somehow, if the Earth were flat, in order for Mount Hood to cast a shadow on the clouds, it has to come down near the ground and then inexplicably curve an angle back up to hit the side of the mountain and then cast the shadow up on top of, or on the bottom of the clouds. How does that happen?
Through our horizon perspective.
Yeah, but how does horizon perspective change the angle of the light?
Because, okay, your sun setting ain't a few miles away.
Sure.
It's many hundreds to 1,000 or more miles away where the sun's actually setting.
Yeah, but that doesn't explain why the angle of the sunlight changes.
It's because our horizon and our sky meet at our eyesight. It's always has been. That's how it works.
But how does that change the angle of the sunlight?
It's how light works in our atmosphere. Have you ever seen the giant red sun during wildfire season?
Sure.
A giant red sun. Okay. Our atmosphere has many distortions to it, which it works out for our vision. We always see our horizon at eye level. You can say if the light puts it 1 degree down or 3 degrees down, wherever you're at. But no matter, you take a hot air balloon ride or anything, your eyes are always going to see that horizon at eye level. The sky meets the horizon at any height.
Yeah, but the sun is significantly higher than the horizon, right? No matter what, it's not, a couple miles above the ground, right?
No, it's more than that because we can't reach it.
Yeah.
But
So-
I don't think it's 3,000 miles away. I think it's much closer.
Well, let's do this.
yeah.
You know what? I measured it. Now you can't see me at all. Is that right?
I see your picture of Mount Hood on the screen.
Oh, you do see that? Okay.
Yeah.
So
Your screen's only like it's tiny. I can't. I might lose you if I jump around and try to bring you back full screen.
Are you on a phone or a computer?
My computer.
You should be able to just make the window bigger.
Let me click on it again. Okay, I got it bigger.
Okay.
Okay.
So you see that bigger. Yeah. Excellent. So here's what I'm gonna. I'll stop sharing that because I want you to see. Let's see. I'll get this here. There we go. Okay. So here we're going to. This is our hypothesis for flat Earth. Okay, not spherical Earth, for flat Earth. Right. There's the flat Earth. That's pretty flat. I used my ruler.
Okay. We can say that's flat.
Right. All right. So now we got our mini Wayne Chipman there on the side, and we got the sun. But I'll do it for Minneapolis. So that's mini tune there. Okay. Now I measured it in September on the day of the solstice. The equinox. When the sun that day goes over what? On the day of the equinox.
I'm trying. I would say it's at the equator.
There you go. That's right.
Above the equator.
Yeah.
Okay.
So now I am in Minneapolis. I am 45 degrees north of the equator.
Yeah.
Right in the middle. It's a good convenient spot that makes some of the math easier. So what I did is in September 21st or 22nd, I measured the angle of the sun at local solar noon. That's when it's highest in the sky, right?
Yep.
That's when it was due south of me. So it's straight line from where I live to the equator, and I'm at 45 degrees north. So how many miles between each degree latitude?
I wouldn't have to know that off the top of my head. I think it's 180, but I might be wrong.
It's 110 kilometers. I don't know how somebody could forget this number. Anybody in the chat know how many miles there are between each line of latitude?
66.6?
No.
Just joking on that one.
It's a little more interesting than that. Oh yeah, everybody's got it. 69, baby. So 69 miles between each line latitude. And I'm 45 degrees north. So we just go 45 times 69. We get 3,105 miles. Okay. So, all right, this is good. This is working out well. So here we go. We've got 3,105 miles between myself and the equator on the day of the equinox.
All
got
right.
that? All right.
Yep.
Now I measured the height of the sun. It was with the small margin of error, about a half degree margin of error, it was 45 degrees above the horizon. So I'll draw that right here. I'll try to get it a little bit to scale. It's not going to be too good because I kind of messed up a little bit there. There it is. So there we go. We've got the sun up here, right there, right? We've got the sun. And the angle, I got to write that down. The angle is 45 degrees. All right, now I'm sure your trigonometry is better than mine. Right? So here we got this triangle here. 45 degrees, 3,105, and then
I think that would put it about 1,505 miles above the Earth. By that,
no,
I may be off. I've just taken half of the 90s up and over.
I was giving you the benefit of the doubt at having studied this for so long, to have your trigonometry better than I do, but it's a 45 90 45 triangle, which tells you what? between the adjacent and the opposite is
Yeah,
the same.
the
They're the same.
Yes.
There
yes.
you go. 3105. There we go. So the sun, if the hypothesis, if the Earth is flat, then as measured from Minneapolis on the equinox, the sun is 3105 miles in elevation. That wasn't a, you could do the same thing. Pick a day. It's easiest on the equinoxes and on the solstices.
Yes, because we know the exact position.
Yeah, you know better where it is those days. So so there we go. We know the sun is 3,105 miles high, at least from that one measurement.
Observation.
Now,
yes.
Here's an idea, Wayne. Call up some other friends at different latitudes. You do this with some friends. I'll do it on the same day, a bunch of you. 5 of you, 10 of you. Everybody in some flat earth group. Do the same thing at different latitudes, at local solar noon. And then measure, just do this simple trigonometry. We teach trigonometry in 7th grade or 8th grade. Like I said, I'm the math teacher and science teacher. So there we are. Then compare your results to see if everybody gets the same sun elevation on the same day. See if that works. That'll be, to coin a phrase, interesting. So so we know the sun now is 3105, at least from this measurement.
From that observation, yeah.
Yeah, so then for Mount Hood, so it's going to vary, I suppose, in your model. It's between 3105 and something else. That's on the equinox. Maybe it's higher or lower at different time. So how is it going to be coming up at an angle then? Because we can calculate how far away from Mount Hood the sun would be at sunset on any day of the year. And it's not going to be more than the entire size of the Earth, right? It's going to be less than 10,000 miles, right?
Yes.
Okay, so let's do that. Let's do the math for 10,000 miles, and we can find out the angle that the sunlight must be arriving at Mount Hood. There we go. We got. We'll round to 3,000 for the sun elevation, right? I know where Robotham got it. He lived in England, southern England, about 45 degrees north. He measured it on the equinox. That's where he got the number. Same as how I got it. So there you go. 10,000 miles. We got our 90 degree here. We got side angle side. You know how to solve side angle side, right?
If I wanted to spend the time getting into the math, I haven't really gone into too much of the math about most of it.
Oh, well, that's a pretty important part of it. So fortunately, I have already pulled up a triangle calculator. I'll share it so you can see it as I do it here. There it is for you. Share it for everybody here. Where did it go? Oh, wrong one there. This will be good. Now we're doing some real science here, huh? We're doing some calculations. All right, so there it is. We've got the triangle calculator. So I need to put in, we got 90 on one side, we got 10,000. And we got this. These are rough numbers, so we can get more accurate numbers if we really want, but they're going to be in the neighborhood, right? So we calculate that. We find out that the angle there is 16.7 degrees. 16.7 degrees. There we go. So it could be more, it could be less, different days of the year. Maybe it's half that. Maybe it's only 8 degrees on the most extreme. But here's what we have. We have the sun here, right here, 3,000 miles high about. We've got Mount Hood here, and we've got 16.7 degree angle of the sun coming down, assuming flat Earth. So how does that light that's coming down at an angle of 16.7 degrees change its angle and then turn and go up so that it casts a shadow on the bottom of the clouds?
The clouds are near you. The sun is distant, light falls. We have a horizon line at our eye level, no matter how very hard. The horizon rises to meet the sky.
But
It's there for anyone to see.
But rising to meet the sky doesn't make the light change direction.
The light falls. Farther from you, the farther it falls down.
It falls. Unfortunately. So all right, so hold on a second. So let me I'll fix my drawing here. That my drawing must be at fault. Okay. Well, I'll start over here. This'll fix it. Right? All right. Do that again. We've got drew that a little crappy there. 3,000. All right, so it falls. Right, so I should curve it going down as it comes, right? Okay.
There are other people who can explain horizon perspective better than I can, but no matter what, where you're at, the horizon, even though it's flat, standing forever, will rise to meet your eyesight.
Yeah, but we're talking about the light angle. So, all right, so here's we've got the Mount Hood here, right? And then we've got the clouds there. But when I made the light fall, as you suggested, we got the opposite effect. Now the light is even worse. It's coming in at an even steeper angle. Not curving to go up so that doesn't work. But I do agree. The light does do that because we do know that the atmosphere is denser closer to the ground. And when you get up 100 miles, there is almost nothing. It's very, very, very low pressure. So we've got this pressure gradient, if you will, which causes an index of refraction gradient. And the index of refraction gradient causes light to bend towards or away from the higher index of refraction. Which one?
You lost me there.
So I'm wearing glasses. Glasses they refract light. That's how they work, by bending it. So air has a certain index of refraction, and our lens has a certain index of refraction. So when light goes from one index of refraction to another index of refraction, it bends. Which way does it bend? Toward or away from the higher index of refraction?
I'd have to look that one up.
It goes towards the higher index of refraction. So in the atmosphere, closer to the ground, we have the higher index of refraction. Up high, we have a lower index of refraction. That means that the light, as it's traveling through the air, will bend down. Just like in your example. You were right when you said light. Well, you said it will fall. It's a little weird way of putting it. It'll bend downward. That's correct. And so what'll happen is actually this: if we have a person sitting here on the ground, they're going to look, when they look at the sun, the angle's going to be coming to their eye different, and the sun's going to appear in a different place. I'll show you what that does.
Well, by your curving to the ground there, like you shown, that would prove that the sun does it underlits the clouds. Because if the light's hitting there in front of you, it's shining up at the clouds.
Actually, the light is pointing the wrong direction here. It's coming and it's hitting the ground at a steeper angle. And what happens is, it's pretty cool. It makes, for the observer here, it makes that observer think that the sun is higher than it actually is. It actually raises the view of the sun. But it doesn't change the angle of the light in the direction that it needs to for Mount Hood to have a shadow cast underneath it. For that, you'd need the light to go, and I can fix that. I can fix it. The problem is it's not going to be backed up by any evidence, but that's fine. That's SOP for FE, right? Am I right?
We tend to believe our senses and what we can see, and if you actually open your mind to look into horizon perspective, you'd understand what I'm talking about. The sky and the horizon converge to meet at your eye level. This is it. That's what it is.
All right. So yeah, but that doesn't address the angle that the light travels. You can't get away from that the light is traveling at a certain angle. So I fixed it. This is what has to happen. There's the sun up there, right up here. There's the sun. And then rather than bending down, as we know the sun does, and as you said it should and does, and I agree with you, now it has to instead somehow inexplicably bend up, so that now it's bending up and it can somehow cast a shadow. I don't know how it would bend up, but that's quite amazing. So since there's no known phenomenon to cause that, it doesn't look very good for flat Earth.
Well, if you drew it in a different way, it would take the observer there in front of Mount Hood, and draw an angle up to his eyesight there in the distance, then draw the sun's angle down to that, and that's the horizon and of the sky and land meeting.
But the horizon,
which is well below Mount Hood.
But all right, I'll draw the guy here. All right, I got
draw from his eyes to where the horizon would be at that point.
Yeah. Okay, so I got
a straight line
right there. You got him right. Right there, we got the guy. All right, I will draw a straight line from his eye to the horizon. Right there. There it is. It's at an angle down.
He'd be looking down.
Yeah, he looks down to see the horizon.
I've never in my life felt myself looking down at a horizon.
Well, you look up at the horizon?
No, I look straight forward.
Oh, yeah.
Always.
Now here's what we could do. We could measure this angle. This angle here, depending on how far away it is very, very
tiny.
Small. Yeah, so this excuse me. So
but I only see the horizon,
like for
3
example,
miles away.
at 45 feet elevation, you're at that angle is 0.1 degree. Now you may not,
okay, hey,
because
Michael,
we've already established that our eye is not a precise measuring device.
Michael, will you hear me out for one little second? Okay. Call me 6 feet tall at my eyes. I'm not that tall.
You don't want me to call you Wayne any? I'm going to keep calling you Wayne.
My son would rather be called 6 feet tall than Dustin, and he's only half inch shy. That's funny. Okay. Standing on the earth, looking out at a perfectly calm day, there's the ocean. Okay. 6 miles away, or no, I think it's 3 miles away. If my eyes were 6 feet above the sand, lap the smooth ocean doing a 2-inch roll at my feet, which I've seen our ocean here do on Long Beach. It's cool when you see the ocean flat like a mirror. It's happened only a few times since I've been here. I see the horizon at 3 miles. It's, as far as I can tell, it's at my eye level. You can say it's 0.001 degree away or whatever. I see it as at my eye level. Now, if on your graph, you take and bring the horizon 3 miles away from where I'm at, then from me to that 3 mile rise of horizon, 6 feet to my eyes, and extend that line out, you have a much different line where the horizon converges. See, you can't just draw a straight line down to the horizon that many miles away and say that's the horizon my eye sees. My eyes see the ocean horizon at 3 miles away. So anything above that has to be higher than that horizon for me to see it.
Okay.
Which puts the sun, to my apparent vision, in a much different perspective compared to the clouds above me.
Yeah, can you go through the math for that then?
No, I can only tell you, it would take me, I could sit down and spend a week or two or however long to do every little
Wayne,
bit of math
let's
about
be
it.
honest, Wayne. You never did the math. Come on.
I've done the math on the drop from level line of sight. And a pilot would have to keep dipping his nose down to follow the curve.
You're changing the topic on us here. You're jumping all around. It's all good. It's all good.
Well, we have horizon perspective. Arguing the flat Earth actually is a moot point.
I know it's silly and pointless, but we do it for fun anyway, just to humor you guys.
Oh yeah, I love it. It's.
I mean, I put debate in quotes because, you know, well, right? You know what I'm saying?
Well, you couldn't even understand what you were saying when we talked about the spinning Earth. That's why I love talking about it, because you have to go to frame of reference, which means everything is viewed as stationary because it's moving together.
Yeah, within the frame. Yeah, we already went over that. So. All right.
And that's what makes talking about the spinning Earth versus the stationary Earth so amusing to me, because you guys don't even know what you're saying. Now, flat versus ball.
Okay. Yeah.
Yeah. Flat versus ball is still funny, but you can't even now. Okay. They've changed their teaching over the years about the spinning Earth, okay?
Oh, since when?
Yeah. Well, they used to teach when I was in school back in the 60s.
1800s? Oh, 1600s. 1600s.
Yeah.
Sorry.
Okay, that the Earth caused the moon phases.
No.
Yeah, they used to teach that.
I'm sorry you had a bad teacher.
Well,
nobody actually thinks that's the case.
Actually, to tell you the truth, a lot of ball earthers out there who don't pay attention to nothing I believe that.
I don't disagree that people don't pay attention in science class. Thus the problem we're seeing right now.
Well,
right? You know what I'm saying? So yeah, you maybe had a bad teacher. That doesn't change that is not the actual position of the globe Earth. That's not the claim, right?
Not now.
And well, it never has
not
been.
Now.
You may, like I said, you may have had a bad teacher, but if you could find a book, like a science book from the 1600s when you were a kid that has that, maybe that'd be interesting. But just your memory as one anecdotal person, thinking that somebody said that, I don't think so. Now I can tell you, as a kid, I had an adult tell me that the Earth rotating is the cause of gravity, which is absolutely not the case.
Oh, some of these morons still say that.
Absolutely, I agree.
So fast.
Somebody told me that, and as a kid, I know the house I lived in at the time. I was no more than 5 years old. I heard that and I thought, that doesn't make any sense at all, because I had spun a bucket with water in it, and I know when you're spinning, it has the opposite effect of what gravity would. So anyway, I got a couple super chats here. Might be good to read. You mind if I read a couple?
Yeah, go ahead.
All right. Oh my goodness. I just made my there it is.
Well, I hate when I type something for a half hour, then accidentally butt my keyboard and it's gone forever.
Yeah. I have not yet disabled my multiple desktops, and so I just accidentally, and I don't know how to get it back because I don't ever use it, to go get the window from the other desktop. So I got to open it up again. Just a second here. We did have Merrick Zayance is a new member. Thank you very much, Merrick, for that. And Merrick, I got to tell you, I had a call with FTFE, and I told him how to pronounce your name. So if I'm right, and if he's right, it's my fault that he's right. And if he's wrong and I'm wrong, it's my fault that
it's still.
I'll take blame. Either way. So okay. He's from Poland, right? Apparently, the last name Zając is an extremely popular last name in Poland. But it's got some letters that us English speakers do not see very often. It's got a cedilla. My goodness, it's taken forever to load. All right, there it is. I'll have a little. I got so many open tabs, you know. It slows everything down when you have that many open tabs. Here it comes. Later tonight, we've got the 10,000 subscriber special, everybody. Doing some giveaways. I got a couple things right up here. We've got this gravity book and this Frisbee here. Signed by McFlatty. My silly cousin McFlatty decided he wanted to volunteer to donate something. Oh, excellent. So it rolled off the screen. Well, we got Zając is a new member. We've got JDT Turbo says, if the earth was round, my shoes wouldn't be flat. So there you go. That is solid. Flat Out, if you know Flat Out, he tested that. He got some 15-foot long shoes that he built and tested for flatness. He's probably the smartest flat earther out there. Have you seen Flat Out?
No.
No? Oh. If you go to everybody, go to his channel, it's Flat Out. Not Flat Out Hero, just Flat Out. He has the biggest pile of evidence ever assembled for flat earth. So we got Connell Silver Fur says, since Asylum isn't here, I'll ask the question for him. Chip, if the earth is flat, why are all aerial navigation based on a globe?
No one uses the globe to navigate.
Oh,
they use flight charts.
Yeah, flight charts are based on globe. Do you know what the Lambert conformal conic projection is?
It don't matter what it is. We use flight paths.
Oh, it doesn't. Now, I happen to have up on my wall here. Now you don't see it. I'll stop the share here so you can see it. Up behind me, I've got these. You see right here these flight charts. You see them?
Yeah.
Up on the wall. What I did is I took and I charted out these flight charts from near Iceland down towards near
I'm actually glad you brought this up because when you're done,
yeah,
I'm gonna put one at you.
Down towards,
you're gonna love this.
Okay, down towards South Africa, and then over near Hong Kong, and each of those, and I use real flight charts that have been used since the 50s. That's these. I just printed them out. You can download them, get them for free at University of Texas online or other places. 3 routes, each route 10,000 kilometers, and a 90-degree turn at each one. So it formed a triangle. Each of the triangle corners was 90 degrees. Now, on a flat surface, a two-dimensional triangle, if you have a triangle with sides, say 1, 1, and 1, what are the internal angles?
Are you talking about where if you left, say, the North Pole?
No. I want to do some foundational trigonometry here.
I'm not even going into that. Are you doing the triangle on the ball thing?
Yes, yeah, that's what it is. I did
with
that.
90-degree angles.
Absolutely, yep.
Yeah, you can do that on a ball.
Yes, and I did. And right here, using real legal flight charts that have been used for decades, I did that.
But they're in the air. They're not on the ball.
So
90 degree. They didn't do that in the air and come back to a central point.
I don't know why that has any bearing on it. That
well, you seem to go into, I can't remember who the guy was who, I want to say Michael Barron got hopped on that triangle on a ball. The 90 degree making a triangle hasn't been done on Earth.
Well, I use the flight charts to plot it out. These are legitimate flight charts that are really used. So are you suggesting that these flight charts are like there's mistakes on them somehow? Or maybe are you suggesting that they're not actually used for flying?
I would say that send me the graph on that because I can't see it too well. Send it to my Facebook. I'll look at closer, but I don't know of any flight charts where they set off at 90, straight down, turn 90 again, and come back to start.
Oh, you mean like real flights?
Yeah.
Oh, well, so fortunately, I did that one as well. There is a flight from Johannesburg to Hong Kong. There is a flight from Hong Kong to London Heathrow. And there is a flight from Heathrow all the way down to Johannesburg. Now, they don't add up to, they're not 90 degrees at each of them. The total of them, rather than being 270 degrees, is 263 degrees. So 3 real flights. The angles between each city sum up to 263 degrees. Now, if the Earth were flat and you had a triangle, what would be the internal angles?
Whatever you want to call it, they're in the air. Here's one. While we're on flights, let's do this one because I'm going to give you the ball. I'm going to give you the rotation. I'm going to give you the speeds, and I'm even going to give you a relative motion on this one. Okay, in New York City, a plane takes off and flies due south. Now, you'd have to, I don't have my globe in front of me, but there's a city on the equator in South America that almost lines up in a vertical line north to New York City. You could probably find, oh shit, Dustin. I'd have to draw it up on the map.
So directly south of New York City?
In South America,
on the
equator is a city. And it's within not too many miles from the same longitude as New York.
Okay.
All right.
There's one called Quito in Ecuador.
I don't think that was the one I picked, but is it real close to the same longitude as New York City, but on the equator?
Yeah, if you go due south of New York City.
New York.
Yeah, I'll get the longitude of New York City. Now I don't know New York City longitude off the top of my head. People will be so upset.
Neither do I. I've got a notebook somewhere here on my desk because I had fun with this one.
All right, we've got negative 74 degrees.
Find out the nearest city on the equator.
There we go.
Sorry to put you through this. It's
just this is fun. It's in Colombia, but there's nothing there.
Go either way.
It's jungle.
50 miles on the equator.
Yeah, you
get 100 miles.
Yeah, if you go west, you get to Quito in Ecuador.
Okay, we can pick that one. I got a different name. I'll try to find it and send you the info. Now, is it close enough you could say it's fairly due south of New York?
Somewhat, yeah.
Okay. Now, say a plane takes off from New York City flying due south to that city.
Yes.
And when it takes off, New York City's going approximately 800 miles an hour due east. So it's got the conservation of momentum. It's going approximately 800 miles an hour due east.
Yes.
Okay, I'm giving you that. Now, it's going, let's go 500 miles an hour. I think they do 550 or something on these international flights, but let's call it an even 500 miles an hour. Okay. It's got the conservation of momentum going 800 miles an hour. It's heading due south in the air, not touching the ground.
Yep.
It's 800 miles an hour due east, conservation of momentum. Well, by the hours that have gone by behind then, that city in Ecuador is moving at 1,043 miles an hour due east, approximately.
Yeah, yeah.
Okay. It would miss that city
Yeah,
by hundreds of miles.
Yeah, if the pilot never corrected the route, it would be an issue. But here's what happens.
Okay, but
yeah,
he's got to make up that 243 miles an hour faster it's moving there.
Yeah, yeah.
So he's not flying due south. He'd have to pick up some serious speed and flying southeast.
So this plane that can go 500 miles an hour it has to pick up an additional westward
243 miles an hour.
An additional westward speed. Yeah, over the course of a 10-hour flight, maybe.
Okay, so he picks up a little at a time.
Yes, yeah.
Okay, now you can't say this pickup in speed is conservation of momentum. Will you agree with me there? Because he only has the conservation of momentum of when he left the Earth.
Yeah, but once... when you hold on. I'll explain.
I love this.
You fly south from New York City. You go.
And you go.
Hold on. Let me explain. You go 10 minutes, right? And over the course of 10 minutes, you need to add a little bit of westward speed. Now, once you've added that little bit of westward speed, you conserve that momentum, and you are still now going. Well, you were going to give me the ball. I don't want your ball, but you were going to give me the ball and conservation of momentum and reference frames and all that. So yeah, that's how it works. This is, again, like I said, elementary school. We teach this.
So it's heading southeast.
Yes.
Okay.
So southwest is
over
where it
a little
needs to
bit
go,
time now. Now it gets some extra conservation of momentum going east. Now remember, this plane's only going 500 miles an hour, and it's already in an 800 mile an hour conservation of momentum loop.
Well, let's call it a reference frame. Let's be correct on the
reference frame. Yeah. Now remember, these reference frames are moving hundreds of miles an hour due east. Now you say it picks up a little bit, and I'm wondering how a conservation of momentum can be picked up when it's in the air. Okay,
well, because the plane has engines. And
it's only going 500 miles an hour.
Yeah, but so what it needs to do
is it has to increase into the 1,043 mile an hour due east.
Yeah, but it has 10 hours to spread out that
little bit at a time. 243 mile an hour wind don't make a difference.
Yeah, but there's no wind because, again,
wind.
The air is moving with the Earth.
Oh, he only had 800 miles an hour conservation of momentum to begin with.
Yeah, but once he moves south, once he moves south, hold on, listen. Once he moves south,
this is where it gets funny.
This is where you stop talking over me.
You don't even know what you're saying.
This is where you stop talking over me.
Go ahead and talk.
You move south, 10 miles south, there's a slightly different reference frame. That air is moving 810 miles an hour, say.
Okay.
And but so all he needs to do, I'm not done talking. All he needs to do is get that slight increase in lateral speed to match that new reference frame. It turns out to act on the plane as a slight lateral force. And the plane only has to add a slight lateral turn to make up for it. Wind is significantly larger than that small amount of lateral force due to the rotation changing. Go ahead.
Okay. Granted, it's small increments all the way down every 10 miles. It just grows. By the time it's reached Quito, I had a different city at equator. It's got a 250 mile an hour wind that is its only increase in speed.
But the air moving at the equator is moving at 1,000 miles an hour instead of 800 miles an hour. So that's not wind.
The plane is not on the ground.
It's in a new reference frame. It's a continuously gradient reference frame as it's moving south.
But we have a 243 mile an hour push of moving air culminated, or the increments culminate in 243 mile an hour air moving this plane east. no longer by conservation of momentum from when it left the spinning Earth.
Oh,
but
why does
only-
conservation of momentum stop?
So 243-mile-an-hour eastward wind. Wind is something a plane can disregard
No, it's
due to conservation of momentum.
like I said.
Think about what you say before you answer that.
It's a new reference frame. The new reference frame has wind traveling with the Earth as well at the higher lateral speed.
And it all acts like everything's sitting still, moving together.
No, there's constant wind all over the Earth all the time. Have you never paid attention to like satellite pictures of the cloud formations? Things are moving all the time. The atmosphere is churned constantly.
Do you realize that air has mass?
Of course it does, yes.
And 800-mile-an-hour air going at each latitude to keep up with the moving ground would swirl around, act still, and they get 80 miles an hour that way, and then 80 miles an hour that way.
Absolutely, yeah.
When it has mass.
Yes, absolutely. Good job. Now you understand why hurricanes travel or rotate one direction north of the equator and the other south of the equator. You just discovered that. Excellent. Good job. Let me do a couple things here. We got holy small. No, I missed a super chat. Somebody said, "Be nice to Chip," and I forgot the rest of it because it's off my screen. I can't bring it up. I've tried, but I'm supposed to be nice to you, Chip. I'm trying.
The girls at the local store are mean to me. No, I love them. They're fun.
Okay, it's Connell Silver Fur says it was the one. So it's Connell Silver Fur. Type it out again. I'm sorry. All right, we've got Holy Smalls as a new member. Thank you for that. JDT Turbo says for $5, if there's a dome and no gravity. Now, we haven't gone over this yet, but I think
I love gravity. That's cool. We're going to get there.
Okay, so if there's a dome and no gravity, what makes the sun, moon, and stars move? It looks like it's a 3-part question here. Also, what makes the seasons, and what's on the other side of the dome? Let's see what we get for that.
What makes them move? Electromagnetic energy, which is what runs our universe. A type of electromagnetic energy that we can't really produce.
All right, so wait. This is amazing new physics. How do we know that this new type of electromagnetic energy does things? How was it measured? Who quantified it? And how was this? What was the hypothesis for this experiment? I'm excited.
Have you seen the superconducting magnets and they make things float by electromagnetic?
Yeah, so like you could get like a 15 Tesla magnetic field and levitate a small plastic ball.
It goes beyond that. They got discs and tracks they can run them on now. It's getting more and more.
But all of those are. Have you noticed those? They dip them in either liquid nitrogen or something else. They need to be super chilled. Yeah.
Yeah.
So and the magnetic field is very strong. They tend to be larger than 1 Tesla magnetic fields. Yeah.
Yeah. Well, that's what our Earth runs on.
Okay, and where is this?
You generate electricity.
Where was this multi Tesla magnetic field? Where is it? Because the Earth's magnetic field is nano Gauss, not multi Tesla.
There's energy surrounding us.
Oh, hold on a second.
We got this. Been suppressed.
I got this from Connell Silverfur says, you need to be nice to Chip. He admitted early on that Eric Dubé is 1 step ahead of him, so you can't understand him to even understand basic math.
Tell him that was a good one. I like it.
Yeah, I mean, you totally nailed all the trigonometry so far, right?
I don't need trigonometry to prove what I'm talking about.
Okay, all right. Well, so here's the deal. You were talking about electromagnetism. So where is how strong is this electromagnetic field? How many Tesla?
I haven't went into that. There's energy all around us. You generate electricity.
Yeah, but you said electromagnetic, and we do generate a electromagnetic field. It's very, very small. You know, like I
Yeah.
said, nano Gauss, maybe, not many Tesla. So how many Tesla is this magnetic field?
It's not total magnetic on drawing on it. We're close to having room temperature superconductors, 0 point energy, and many more things that actually exist and are patented.
Okay, but how does that make the sun, moon, and stars move? Where was this experiment done? What was the hypothesis for this experiment?
Okay, I love this one. For a moment, pretend we have the perfect superconducting magnet.
Okay.
It's called a magnet, okay? The perfect energy field. And Einstein's, I think, things, or Newton's, or whoever the hell.
Somebody.
Things set in motion. Things set in motion stay in motion.
That was, yeah. Pretty good. Newton's first law.
Okay.
Close.
So we have this perfect superconducting magnet and the perfect superconductor, and it was set in motion, and it's eternal. Look at our seasons. Our stars come back to the same position.
Where is this superconducting magnet at?
It's a torus field that surrounds our Earth.
Okay. Where is it generated?
Well, I think it has two generators. We have two rotating star circles, which have been proved by the equator films or of star trails. Yeah, many things can go in on this.
Yeah, that's a problem.
They generate the energy, and
so all right. Yeah, but I'm still trying to get.
We're going into a lot of theoretical.
This isn't theory. This is you were saying this with certainty.
Right? Yeah, I'm pretty certain it's there.
Yeah, so
been there from the beginning.
So there's no question that the Earth has a magnetic field. The north magnetic field is near. It's in the Arctic Circle, and the south magnetic field, our pole.
And how do you feel that's created?
So the south magnetic pole is in the ocean south of Australia. So
yeah.
So you're explaining to us how on flat Earth this is created, but that can't be what you're talking about that makes the sun, moon, and stars move, because that's very weak in comparison to the type of thing you were talking about for these superconducting super magnets, because they're in the range of multiple Tesla. Do you know when I say Tesla and Gauss, do you know what those are? No?
I don't zero in on any one little thing. I spend a lot of time looking at the overview.
I believe you.
Okay.
Yeah. So yes. Here's the deal. A Tesla is a measure of a magnetic field. It's a very large amount of magnetism, actually. Because it's such a large amount of magnetism, people decided, let's not use things in Tesla all the time, because it's all you're going to be dealing with is millitesla and nanoteslas. Let's divide it by 1,000 and call it a Gauss. So 1 Gauss is 1,000 Gauss is 1 Tesla. The Earth's magnetic field is much smaller than 1 Gauss, I believe. Pretty sure on that. The magnetic field in these examples you're talking about, where you're levitating plastic or have these superconducting super magnets, whatever, that they're well
beyond levitating plastic.
They're very,
they're well beyond that.
Yeah,
there's videos of them,
but they're typically 1 or 2 Tesla strong. So the Earth's magnetic field is significantly less than that. So
yes,
how is the sun? I figured you must mean that the sun and moon somehow are locked into an electromagnetic channel somewhere, somehow. Where is this channel? How strong is it? And how is this confirmed?
No one's confirmed it. How do you? Okay,
Oh,
you
so
want
it's
to
just-
talk about
it's just-
confirmation
It's just a guess. then.
theory? Or,
All right.
oh,
No, all right.
that's
fine.
what everything is. Okay,
Well, you
now
start.
we're
You
on to
start with
gravity.
you can start
Oh,
with a
wait,
guess.
no.
Hold on. We got a 3-part question here. You can start with
Okay.
a guess, and then you form a hypothesis to calculate the
Well,
ramifications of
which
that
is
guess,
what the
and then you
ball earth
test
has.
it. And then you test
Yeah.
it. And if you
Yeah.
test it and it doesn't work, then you throw out that hypothesis. It's wrong. But if you test it and it does work, then it's confirmed, right? And it's a very strong possibility. So
Okay,
that's how you
how
do
can
things.
you test? How can you test the celestial bodies?
I don't know. I'm just if
No one
you're,
can.
You're the one that was
No one
making the
can.
claim. You're the one making the
so
claim.
does science. So does science. How do you test the celestial bodies?
Well, that's up to you, I guess, to figure out how to do that.
But no one can figure that
as
out.
a flat Earth scientist. Are you consider yourself a flat Earth scientist?
I guess I can be a scientist because I have as much study as anyone does in anything
All
on
right,
it.
so
Pretty
you're a
much.
flat Earth scientist. I need to correct myself. George Natchik, who is much more likely to be correct than me, says that it's 10,000, not 1,000, as the ratio from Gauss to Tesla. So I will at this
Okay.
point say you are more likely correct than I am, but everybody look it up yourself.
Yep.
Okay,
I
so JDT Turbo's second part of the question: what makes the seasons?
well, if you've ever looked at any flat Earth simulation, you'll know that the Earth is like a light circling above our circle flat Earth, and it changes throughout the year and creates and goes above the equator and south of the
Did
equator.
you just burp? Come on,
Yes,
come on,
sorry.
my goodness.
Sorry.
We are much classier than that here.
Hey, sorry. I ain't used to wearing a microphone. I actually looked away from it, but didn't realize it went with my head. I
That's
got
all
one of
right.
them earphone things with the little thing coming down. Low tack. Sorry. And it moves in and north and south of the equator. And the analemma, I used to know how to solve those, but that was a long time ago. I'd have to learn it again. They're fun. But the analemma alone proves we live on a flat circle Earth.
All right, well, yeah, that's a different topic.
The
So
analemma.
let's stick to the seasons. What causes the sun? You're saying the sun goes in tight circles and then to bigger
larger
circles.
circle above
What-
and south of the equator.
What causes it to change its diameter of its
Circle
circles? Yeah, however-
above our Earth.
Yeah. What's the
It's
cause?
it's got its eternal motion set in it. Doesn't change.
Yeah, but that's not
It does not change.
that doesn't explain the cause. What makes it happen?
Back to electromagnetism, beyond which we can understand. You could go into quantum energy, all that, whatever you want to call it, and it's got its set path and course.
So you don't
That's
know.
been programmed.
So
Neither does science.
you're just the thing
Neither
is
does science.
the science doesn't understand anything about flat Earth because it's not testable.
They don't understand anything
it-
about our celestial bodies.
Oh,
They're all
well,
guesses and ideas.
I beg to differ
and
on
you
that.
say,
but,
Mike, well,
right.
where's the proof that
I'm
our
sorry.
sun is a flaming ball of hydrogen 93 million miles
Oh,
away? I
my
mean,
goodness,
where's any proof
that's
of
a fun.
that?
Let's review that again. Where's the proof that the sun is a flaming ball of hydrogen 93 million miles away? First of all, science doesn't prove things. There are 4 places that I know of that proof happens. Pure logic and math. You can prove
Yeah.
things in there. Measuring the purity of alcoholic beverages.
That's, yes.
Baking with yeast. I made bread today. It proved for a
Yep.
while.
Cool.
And then the 4th place that people talk about proof is in pseudoscience. Science doesn't prove things. It finds evidence for things, but there's always a possibility that it can be improved. Always. So
Yeah.
where did something get
So it's
proven?
guesses
It wasn't
and
proven. So
ideas.
we measured it, we did things with it, we had a hypothesis, it was confirmed, we did over and over and over. And over time, these things all added up and they were confirmed. And you get this big bunch of evidence that all fits together and meshes together nicely. That then, in science, people are like, we're extremely confident about that. So when you say proof, I'll swap in extremely confident about something. So how did we get extremely confident that the sun is a flaming ball? So it's not flaming. What is it actually? Do you know that it's not actually flaming? That's not the claim?
It's, I think, nuclear fusion on a large scale.
There you go. All right, so it's not flaming. Okay. So
it's an immense ball of heat. Can we gather that?
And fusion is happening. So how did we gather a whole bunch of evidence that the sun is doing this nuclear fusion? Well, based on the
spectral analysis of our atmosphere looking at the sun. That's one.
That's one, absolutely. Another is by looking at the nuclear reactions that happen that we've done here and saying, well, if this is happening in the sun, then we would expect to see different things, different behaviors coming out of it. For example, we expect to see a certain amount of neutrinos coming from the sun. Look at that. We measure it. We find that's about correct. We say, well, there should be a certain quantity of photons coming, a certain intensity. We measure that. Oh, look at that. We find that. So a bunch of different things like that people have done to confirm all these different ideas that they had about what the sun must be doing and say, you know what? We got a whole bunch of matching evidences, a whole bunch of different things. Now, how far away is the sun? I love this one. In the 50s, there were several different times that people that sent radar. They bounced radar off the sun. They had a 40-mile square or long, it's a rectangle, of wire as the antenna to send this signal to the sun. And it's on my website, mctoon.net/sun. If anybody wants to look, I have 2 of them listed there. They sent radar to the sun and it bounced back, and it took just under 1,000 seconds, about 980 seconds, for the radar signal to go from the surface of the earth and then be read back again. Now they encoded it in a particular way so that when that came back, they got that same signal back. Pretty cool.
Oh my God. So do you know what you just said?
Yeah.
The radar signal they sent.
Yeah, they sent a signal
to the sun and back.
Yes.
In 987 seconds.
980, about, yeah. What about it?
I was just having a little fun in my mind with that one. Now, when you look at the speed, how we're circling the Earth at 66,000 miles per hour, approximately, almost 67,000 miles an hour, we're moving around the sun.
Yeah, that's
you
true.
with me?
Yep.
Okay, and we're spinning, depending on where they're at. I imagine it might have been the USA. Let's call it 800 miles an hour due east. How did that radar signal hit that moving sun, which is moving 500,000 miles an hour, while we're moving 67,000 miles an hour and 800 miles an hour in a spin, and come back to these same receptors?
All right. So
without missing them by thousands of feet or miles or hundreds of miles.
Yeah, well,
that amount of time.
Of course, your question goes back to some confusions with reference frames, but it doesn't really matter that much.
They all wax motionless because it's taken in the same amount of reference frames.
It doesn't matter that much. Yeah, I do. I love it too. So here's the deal.
I love it.
the signal, it's not like it's not a laser. It's not super narrow. It was a giant, extremely powerful radar signal that went sort of in the direction of the sun. And it bounced back sort of in the direction of the Earth, but everywhere, huge distances to the side of the Earth received that same signal, not just this tiny little beam. So that's not a challenge at all. The cool thing is that if 980 seconds about, you divide that into, you get about, let's call it 1,000, you get about 500 seconds one direction. Are you a fan of One Direction?
We're getting down to 8-minute sun. I know this.
Yeah. So 500 seconds, you calculate knowing the speed of light, and you get 93 million miles in 500 seconds. It's amazing. 2 different experiments did the same thing, same amount of time to bounce the signal to and from the sun. It's awesome. Absolutely awesome. Very simple to understand too. No trigonometry in that one, right? There are some different ways that people have measured based on angles of Mars, the moon, Venus, other things like that. That involves trigonometry, which you can't do. So this one's easy. You just need to do about 5th grade algebra, solving for one variable. So there we go.
If you ignore all the other movement. Now,
yeah. All right, now hold on. We got one more.
Yeah.
Because JDT Turbo is really getting the worth out of this one here. Also, what's on the other side of the dome? Assuming you think there's a dome.
There is a dome.
Okay.
Rainbows prove it. What's on the other side of the dome? The water's above.
Oh. Okay.
Science don't know. They can't get past the dome.
Science knows there's no dome, but...
Do you believe we landed on the moon?
In fact, I met Charlie Duke, who landed on the moon. Underneath there, I got the book that he wrote and he signed. So I can send you on Facebook. I'll send you a picture of myself with Charlie Duke. So, all right.
But do you actually believe we landed on the moon in 1969?
Absolutely, yeah. It was amazing.
Okay, now, here's what's funny when someone actually sent me their flight path. It's like a 5-year-old drew it. For all the movement involved. Because back in 69, people didn't know about, you got to give me a little bit here, okay? Let me talk.
I'm just going to give a preview for the audience. It's going to be frame of reference misunderstanding again. All right, go ahead.
Again, I love frame of reference. It's everything's motionless because it's in the same frame of reference. I love that. Okay. All right. I'd love to see the trajectory and flight paths mapped out because we have a moon that supposedly is circling us once a month. That's another funny subject. Okay. Add in that speed. Then we have a sun that is dragging us along at 500,000 miles an hour through the universe, and an Earth that is circling the sun at 67,000 miles an hour while it's spinning once a day, which is anywhere from 800 here to 1,000 equator. Send a rocket off. And I think wasn't its top speed around 18,000 miles an hour or something like that? Or I don't know.
Yeah, I don't know off the top of my head the top relative to the Earth's speed.
Well, with 18, whatever the Apollo rocket went, plus 800 miles an hour for a spin. What is their planned flight path to achieve this? With 69 technology and everything. I mean, anyone can go online and see all the fakery of the moon landing.
So basically you're saying you don't understand, therefore fake. That's what it sounds like to me.
Produce the flight path they planned out to achieve this.
How did they do that? Well, the thing is, because of reference frames, they don't need to worry about the sun traveling through the galaxy, right? You only have to worry about
spinning or the 67,000.
You're right, absolutely. All you need to worry about is the relationship between the speed of the Earth and the speed of the moon. Everything else, because you're in the reference frame, can be ignored. It's fantastic.
I love that.
It's still plenty complicated.
It's like
So, all right.
frame of reference. I love that. It's like the parent telling the child, well, Santa Claus just magically squeezes down that chimney and comes out and gives you presents.
Actually, no, because remember,
Ugh.
we teach conservation of momentum in elementary school, and
Yeah, I know.
reference frames maybe in high school. So
Yeah.
it's not. Nobody but you seems to have a problem with this. So, I mean, we
have everything's moving, but we take a reference frame.
We've got 250
so
people in the
it's
chat,
not moving.
and they're following along saying, what the hell's wrong with this guy? Why can't he understand reference frames? But, you know, that's you. You do you, man.
Reference frame saying
you
got to pretend everything's motionless.
You're within the reference frame. Yeah, absolutely. Yeah. You now understand reference frame. Congratulations. Okay, we've got...
Oh, my God. Okay.
Esteban.
Here shit.
We got Esteban Ilbaca says planes push off the atmosphere. That's at ground speed. There you go. Oh, Man Devil's
planes push off the atmosphere. Yes, I agree with that.
Man Devil is upset that you're a Santa denier and he wants me to kick you out.
Tell him he better leave me some effing cookies because my beard's turning white.
You know there are 4 parts to a man's life. You know about that?
That you walk on
your
hands and knees.
Not that one. No. When you believe in Santa, when you don't believe in Santa, when you are Santa, and sounds like you, when you look like Santa. So
I love that.
All right, yeah. So
that one's funny.
Esteban is saying the planes push off the atmosphere, and the atmosphere is at ground speed or approximately ground speed. So yeah, that's the reference frame. We got Mark Wagner. This sounds good. He says there is no speed compensation for east-west, not a factor, not part of flight planning or execution. Weather mixes it all up because the weather is a much stronger force than the Coriolis force. So there you go. And you seem to understand it now, so that's good. Congratulations. We got a new member. I only want to talk about celestial poles.
They got strippers on them?
Not that kind of pole, Chip. Come on, Wayne.
I'm having fun.
This is a family show, Wayne.
I've been celibate for over 10 years
I don't want to hear about it. I do not want to hear about it.
Oh, that's too funny.
Connell Silverfur says, Chip, simulations require math. Blurfs hate math. Do you hate math?
No, I love math.
Okay. Because I was going to ask you, where did the math touch you? But that's not going to be necessary. Connell Silverfur is a new member. Thank you very much, Connell. We got Asylum says, why is all navigation based on a globe? Again, with that one.
They use charts.
Yeah, and they're spherical charts, actually. But
no, hey, buddy.
Here's the challenge.
If you guys got drunk and fell down with a chart over a globe, I'd have to say, hey, guys, straighten out, put it on the desk.
It does sound like you're drunk a little bit. All right.
No, I got a buzz.
Here's the challenge for you, Wayne. Take these charts I got here, print them out, universityoftexas.edu, utexas.edu. Print them out, tape them together, and see if they're flat. In fact, I'll pay you $10,000 if you can tape together maps, real maps, and I have that on my website, and they lay flat. I'll send you that one.
I'll have to look into that.
And the cool thing is, I am not the sole judge of this competition. It's not me. If you disagree with, if you submit a solution and don't like it, then the judging passes to a judging panel of 3 people. So out of my hands. It's pretty cool. because I'm confident. I don't need to be the one to judge and just say no. So, all right, we got Justin and Greek letters. Who wants to tell Chip that entropy throws a stick in the spokes of Chip's perpetual motion electric universe beliefs? Entropy does tend to do that.
Yeah, everything's dying.
The 0 point energy is untestable. So anyway, that's fine. All right, thank you for that, Justin. We got Asylum. Wayne, offer from me to you. This is pretty nice of him. Come to Sydney, Australia. I will show you how to chart a flight and how to fly an aircraft. You won't be a flatty afterwards. You just got to get yourself to Sydney.
He knows I don't like to fly.
Oh, that's right. Well, there's boats. You're in Washington, right? You're in Washington. You jump on the boat, get yourself down to Sydney. There's a port there, right? That's easy. That's like,
Michael.
Yeah.
There's too many guys in Sydney who want to beat me up.
What the hell did you do in Sydney?
Them fuckers are upside down.
From your orientation, they are. All right.
Yeah.
Let's see. We've got Justin says ring rainbows appear below you when you skydive from a high altitude. Is that supposedly above the so-called dome then? Have you seen these
skydivers seeing rainbows below them?
Yeah, a full circle all the way around.
Well, they had to have one of them fisheye lenses to make that.
No, it's just a regular lens. Like you look down, you see the ground, all of the ground below you, and you see a rainbow in a full, complete circle.
A circle below you.
Yes.
We live on a circle Earth. Yes. If they say that can happen, I agree with that.
But how is that only possible if there's a dome? What mechanism is it prevents non-domed areas from experiencing that?
No, I haven't. You can look into this. I don't think you can make a rainbow without a glass reflective surface involved.
Really?
Just my conjecture. Look into that. See if it can be done without any form of glass being involved anywhere.
So would you? But all right. So what if? That's just hypothetical here. What if I were to show you a rainbow that didn't include that? What would you say then? What is the requirement that only a dome can cause a rainbow? How did you come to that, to be in that position?
I did not claim that's the only.
You said it was proof.
What I said was I'd be interested in seeing if anyone can produce a rainbow without any form of reflective surface involved.
Yeah, but my question to you isn't about that. My question to you is why is a rainbow only possible if there's a dome somehow?
A reflective surface.
Well, why?
I just think that. I'm not saying that's the case.
It's not proof.
This is just a conjecture I'm putting out.
Okay, so why would you do that then? Because
I think you need a reflective surface to create a rainbow. Is what I feel.
It's just a feeling. Come on. You got to do more than that, right? You want to have some science to it. You want to have hypothesis. You want to be able to test it, right? So here, I'm showing it to you now. Let's see. I'll get it up here so everybody at home can see. Where is
I see a guy sitting down.
Yeah, there's a kid sitting down there. All right.
Something up.
Yep. So here we go. In his garage, this guy's got, you see that pipe there? That's a PVC pipe. So you've got right there the light, right? Just a little basic light.
Yep.
Right, and then he'll pan across. We'll see the Right there, you can see his the window way over there. You can see it's shining, so the light is shining here, and then this pipe has a bunch of holes in it, and water is spraying out of it. And
Oh, that's pretty cool.
And there's a rainbow. Look at that.
So it can be done.
Absolutely. Isn't that awesome? I love this one. This is pretty cool.
Yeah, that's pretty cool.
All right. So, we got a couple super chats I got to work through. I got my 10,000 subscriber celebration coming up in 7 minutes. So Wayne, we're going to have to wrap it up here actually kind of quick.
Yeah. No, this has been fun, Michael. I love this.
Yeah. All right. Hey, you're a good sport. I saw you with Fight the Flat Earthers a little more contentious, but
he got a little mean at times, and I don't see why that has to be done. I mean, he does, got bad.
I talk to him every once in a while. I'm like, hey, cool your jets, man. He's like, yes, sir.
Yeah, I mean, I think you're funny at times when we talk spin, but as far as the defending the ball versus flat, I have to put my hands off and tip my hat to you. I don't got my hat on, but I got to tip my hat to you on that. You did real good. Now the spinning versus motionless, I got to say you got silly, but so I'll let you have your own opinion of that.
Do this. Can I suggest this? Look up either reading or on YouTube. What I like to do is I like to find lectures.
I'm trying to find a pen.
Find some lectures on reference frames. That's what I do. I was working on. I installed a whole new hardwood floor in my kid's bedroom this weekend, and all weekend I listened to lectures. So, all right, let me keep going here. I got a couple more before we go.
I love YouTube. I feel I cheat. I learned new trades in a few days that would take men.
Oh yeah, I
years to learn them. I love YouTube on how to you learn.
I could never fix my car without YouTube. So.
Yeah.
All right, Chip, what makes celestial poles on the globe model? That's a different different question.
Celestial poles?
Yeah, the two celestial poles, the North Celestial Pole, the South Celestial Pole. What makes that happen on the globe?
Then we come into the refraction of our dome.
No.
Here,
on the globe.
Out,
on the globe, not on flat Earth, on the globe.
Oh, the South Celestial Pole disproves the globe. Because at certain times of the year at night, different sides of the globe, almost to a half, will see the Southern Cross at the same orientation where their eyes are, but it should be flipped upside down if they're on a ball looking at it.
Wow.
Have them look into that. Yeah.
That's amazing. There you go. There you go. I only want to talk about celestial poles. That's your answer. I don't know where you're going to find the information on that, but that's your answer. All right,
it's been argued a few times. But yeah, they could not see it in the same orientation of the sky with across the short part up facing them just like the other side would, because they would see it at a different side at that same time of night. Only during certain times of the year when they both have night in that same hemisphere.
Okay. Of course, if the Earth were flat, we would expect to see a large lateral speed at the southern extremes, not a center point circling around it. But that's a different topic. We need to move on. We say Asylum says, how do I calculate distance on flat Earth? So distance between 2 points, Wayne. How do you calculate the distance between 2 points?
Or flight charts on our shipping lanes.
Yeah, how do you calculate those distances? Because they need to know when they plan for how much fuel they load up in the plane or in the ship. How do they know the distance?
We have our flight charts. Look at the world and watch all the flight charts.
Yeah, but how do you calculate the distance? I'll give you 2 points on the surface of the Earth here. 2 points, and how do you calculate the distance between them?
Because they've done it over and over and over. all our shipping lanes.
How
They found
did they do it?
now trial and error in following the North Star, which is our central point for thousands of years, Polaris, which would not be possible on a spinning, moving universe. Look at the math and the spiral of our Earth.
Wait. It doesn't, it's never moved?
It's been our central point for thousands of years. Look back. What do they always look at? Our ancient mariners.
No, but I'm sorry.
They looked at the North Star.
But it has the North Star been completely fixed and not moving for thousands of years?
Oh, it has a tiny off-center wobble. Tiny.
But
very tiny.
But has it moved position?
No.
Are you sure?
Well, now you're looking.
Do you have any evidence to support that claim?
Do you have any evidence that it hasn't?
It's on screen right now.
That's what people say.
The nautical almanacs have been published every year for centuries. They document the position of the stars. It's very vital that they're correct because navigators use them to get their bearings. So in the nautical almanac from 1850, Polaris was not at 90 degrees. It was not at 89.5 degrees. It was at 88.5 degrees. So in 1850, Polaris was an entire 1.5 degrees off of center. In 1900, 50 years later, it had moved to 88 degrees 46 minutes, so about a quarter of a degree closer to the center. By the year 2017, it was 89 degrees 20 arc minutes. So about just a bit over, just a bit under 3/4 of a degree. And right about now, it's been a few years, it's getting very, very close to just a 1/2 degree off. So over the course of 150 years, about a little more, it's moved 1.5 degrees. 1 degree. So it does move.
Yeah.
It has been moving for thousands.
Set pattern.
It has been moving for
you
thousands.
Only gave
you said it didn't move. We can go back farther.
I said it moved a little bit.
Yeah. All right. Well, that's fine.
Now, if you want to go back thousands of years, who has this proof? It has its cycle. Our seasons work on like a 13-year reset where they go through their whole celestial movement and they come back to the exact same position. And they do this over and over and over. And it can be recorded. You can set a telescope.
But you don't have the problem is you don't have the predictive ability to like look at it and then predict where it's going to be. You just say, oh, it was there in the past, therefore it's in there in the past.
That's how NASA predicts everything off the previous movements.
Actually, no. Actually,
that's what. Oh yeah, they do.
It's been modeled. You can actually look at the source code for Stellarium, an open source software that has all of this modeled out. Or you can use, there's a Python library as well. All open source. Anybody can have a look if they want.
Get me this. We have our ancient stone monoliths with little holes that line up with the sun.
And what's the margin of error of those? How precise is that measurement?
Oh, I'm not worried about precise measurement.
But
I'm talking thousands of years.
I'm worried.
And it still comes through. And yes, there's a slight wobble because all of them have their set path.
Yeah, all right. I gotta move on, buddy. I gotta move on. So I got Asylum says,
hey, love you.
So he says,
love you guys. This has been fun.
I got 2 more questions. 2 more things. We got Asylum says, so I take it my offer was rejected. That was to come to Sydney. So yeah. And then the final one, we've got Wacko in Seattle. There you go. He says, is he in Washington? I'm in Seattle. Where should I not go? Where should he not go?
Seattle. I live on the beach. You couldn't pay me to live in a city right now. It would be a bad thing.
On the beach. Excellent. All right, Wayne.
Yeah.
Thank you very much. It's been good. We'll see you on Facebook, I'm sure, and maybe you want to come back. Anything you want to say as you leave?
I love all you guys. This is humanity. I love this. This is fun. I only tell people, hey, here's what I've learned. I'm not the smartest tool in the box, but I do okay. Just research, look into. Our whole history is a lie. All of our history, it's a lie. What we were taught.
All right.
Look at the rocks we move, and the stones the ancient moves. Ours are little tiny pebbles that a kid would show you and feel him proud he brought it home. Well, they have these huge blocks that we can't even move. Think about that. And I'll leave it on that.
All right.
We're humanity. I love you, Michael. And if I've been mean to you, don't feel bad. I'm mean to everyone. My best friend thinks I'm an ass.
This is one of the more entertaining and fun ones. So thank you very much, Wayne. Everybody,
I loved it.
Everybody else, I do have a 10,000 subscriber special coming up. The couple people, Glober Mom has put it in the chat. And we will see you all in that one in just a couple minutes. I'm going to have to go to the bathroom. So.
Okay. So, tell them if they don't hit 10,000, I'll hunt them down.
I already hit 10,000, man. I'm there.
Oh, God.
I need 20. All right. So we'll see y'all later. Bye.
Hey, Mike, it was fun.